Hello, friend. Welcome to Science for Sleep. Whether you have returned tonight or are discovering this quiet corner for the first time, this is a place to slow down, learn something gentle, and let the day slowly loosen its hold. Tonight, we are traveling across some of the strangest places on Earth. There are pools colored yellow, green, and rust red, stones that move across a desert floor, forests growing at the bottoms of enormous holes, and caves large enough to hold rivers and clouds. Some of these places look like scenes from another planet, but none of them require impossible forces. They were built from familiar materials, including water, rock, salt, iron, sulfur, ice, air, and living cells. The strange part is what happens when one condition becomes extreme. Water may grow unusually acidic. Salt may become highly concentrated. Pressure may build deep below a lake. A population may remain isolated for millions of years. Earth formed about 4.5 billion years ago. It has cooled greatly since then, but its interior is still hot. Some of that heat remains from the planet's formation, when pieces of rock and metal collided and joined together. Some is produced by the slow breakdown of radioactive elements inside the planet. That energy helps drive volcanoes, earthquakes, hot springs, and the movement of tectonic plates, the enormous slabs of crust beneath our feet. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find this calm corner of science, one sleepy listener at a time. From the surface, Earth can seem calm and finished. Yet continents continue to move by a few centimeters each year. Mountains rise and wear down. Rivers cut valleys while glaciers grind rock into powder. Ocean water enters cracks in the seafloor, warms near hot rock, and returns carrying dissolved minerals. Rain absorbs carbon dioxide and becomes slightly acidic. That weak acid can slowly dissolve limestone and help create caves containing underground rivers. More than 70% of Earth's surface is covered by ocean. Below that water are plains, ridges, volcanoes, canyons, and trenches. The deepest known part of the ocean lies almost 11 kilometers below sea level. On land, salt flats can cover more than 10,000 square kilometers, while giant sinkholes can descend more than 600 meters. These places can feel unrelated, but the same processes appear again and again. Water carries material from one place to another. Heat changes which minerals remain dissolved. Evaporation removes water and leaves salt behind. Oxygen reacts with iron and creates red and orange compounds similar to rust. Pressure keeps gases dissolved in deep water. Isolation allows animals and plants to change along their own path. Time enlarges every effect. A small amount of limestone dissolving each year can eventually become a cavern. Salt, left after repeated floods, can build a white plain visible from space. A slow shift in the crust can deepen a lake for millions of years. A few seeds reaching a young island can begin an ecosystem of plants, insects, and nesting birds. Earth's strangest places make ordinary processes easier to see. In a garden, iron oxidation may appear as a thin stain on a tool. At bloodfalls in Antarctica, related chemistry colors an outflow at the edge of a glacier. In a kitchen, salt may remain after a drop of water dries. In Bolivia, repeated evaporation helped create Salar de Uyuni, the largest salt flat on Earth. In a bottle, carbon dioxide stays dissolved more easily under pressure. In Lake Nyos in Cameroon, gas accumulated in deep water until a sudden release in 1986 showed how powerful that same physical rule could become on a vast scale. Understanding these places begins by looking closely. A color may reveal a metal. A crust may reveal vanished water. A line in mud may reveal movement too slow to notice. A forest far below the surface may reveal a cave roof that collapsed after water dissolved the rock beneath it. The first clues are often visible before the mechanism is known. Among the clearest are the colors written across the ground, where sulfur, iron, salt, heat, and water turn Earth's surface into something almost unrecognizable. At Dallol in northern Ethiopia, the ground can appear yellow, green, orange, and deep red within only a few meters. The colors look almost painted on, yet each shade points to a different chemical condition. Bright yellow crusts can contain sulfur and sulfate minerals. Red and orange patches often form where iron has reacted with oxygen. Some green pools contain copper compounds dissolved in the water or deposited around their edges. Dallol lies in the Danakil Depression, within a wider region called Afar. 3 large pieces of Earth's crust meet there: the Arabian Plate, the Nubian Plate, and the Somali Plate. Their boundaries form a spreading system where the crust is slowly stretched and thinned. Heat rises more easily through this weakened region, warming underground water and feeding volcanic activity nearby. The surface also contains thick layers of salt left by ancient seas and repeated evaporation. Water enters fractures in the ground, moves downward, and becomes heated. As it passes through rock and salt deposits, it picks up dissolved minerals. The hot fluid later rises toward the surface, where pressure, temperature, acidity, and contact with air begin to change. A dissolved substance can then precipitate. Precipitation means that material leaves the water and becomes solid, forming a crust, crystal, or fine mineral coating. This process acts like a slow chemical sorting system. One mineral remains dissolved under intense heat. A second forms when the water cools. Iron changes color after meeting oxygen. Salt collects when water evaporates. Nearby pools can therefore look completely different, even when they sit within the same hydrothermal field. Some Dallol pools are extremely hot, acidic, salty, and rich in metals. A few studies have reported microorganisms in parts of the wider region. Other research found no clear evidence of active life in the harshest pools. The conditions vary sharply over short distances, so one result cannot describe every spring, crust, or brine. Water chemistry produces another red landscape thousands of kilometers away in southwestern Spain. The Rio Tinto flows through a region rich in iron and sulfur minerals. Its water can be as acidic as vinegar in certain stretches, though the exact value changes by location and season. Dissolved iron gives the river part of its red-orange color. When iron reaches conditions where it can react with oxygen, it forms rust-like compounds that settle on rocks and along the riverbed. Microorganisms also take part in the system. Some gain energy from chemical reactions involving iron or sulfur, rather than from eating plants or other animals. Scientists call them chemolithotrophs. The name refers to life using energy from inorganic material, meaning substances that do not come from living tissue. These microbes can help convert iron and sulfur into new chemical forms. The river's appearance also reflects the local geology, natural weathering, oxygen exposure, and thousands of years of mining. Copper, silver, gold, and other metals have been extracted from the Rio Tinto region since ancient times. Mining opened rock to air and water, increasing the area where chemical reactions could occur. A similar red color appears in one of the coldest landscapes on Earth. Blood Falls emerges from Taylor Glacier in Antarctica's McMurdo Dry Valleys. The outflow begins as a dense, salty brine hidden within and beneath the glacial system. Its high salt content lowers the freezing point, allowing some water to remain liquid below 0 degrees Celsius. The brine carries iron collected through contact with rock and sediment. While trapped beneath the ice, much of that iron remains in a form that does not create the familiar red stain. Near the glacier's edge, the brine reaches oxygen. The iron then oxidizes and forms reddish compounds spreading across the pale ice. Warm, acidic river water and freezing Antarctic brine can therefore produce similar colors through related iron chemistry. Blue appears through a different process at Kawah Ijen in eastern Java, Indonesia. The crater contains a highly acidic lake and openings that release sulfur-rich gases from the volcanic system below. At night, some of those hot gases meet oxygen and ignite. The flames can burn with an intense blue glow. Liquid sulfur may also flow for a short distance after the gases cool and condense. The blue light comes from combustion, meaning a chemical reaction that releases heat and light. The molten rock beneath the volcanic system is not blue. Sulfur flame creates the color seen on the crater's dark slopes. Across these places, color records changes in heat, oxygen, acidity, salt, and dissolved metal. The ground begins to look less like a random painting and more like a chemical map. When mineral-rich water continues to arrive and then repeatedly disappears, its colors can fade into something even larger. A white landscape built from everything the water left behind. When mineral-rich water spreads across a wide basin, the scale of the process changes completely. In southwestern Bolivia, Salar de Uyuni covers more than 10,000 square kilometers. It is the largest salt flat on Earth. The surface sits roughly 3,650 meters above sea level on the Altiplano, a high plateau between branches of the Andes. From the ground, the salar can seem almost endless. From orbit, it appears as a bright white shape large enough to stand out against the brown mountains and volcanic plains around it. Its unusual flatness developed through repeated flooding, settling, and evaporation. Water entering the basin spread across a broad, shallow surface. Fine clay and mineral particles settled into low areas. As the water evaporated, dissolved salts form new crusts over the basin floor. Countless wet and dry cycles gradually reduce small differences in elevation. Some measurements have found changes of less than a meter across much of the salar. Uyuni lies inside a closed drainage basin. Scientists sometimes call this an endorheic basin. Water flows inward from surrounding slopes, yet no river carries it onward to the ocean. Rainfall and snowmelt move through volcanic rock before reaching the basin. Along the way, the water dissolves tiny charged particles called ions. These include sodium, chloride, lithium, magnesium, potassium, and boron. When the water reaches the low ground, several things can happen. A small amount may seep underground. Some may collect in shallow temporary lakes. Most eventually returns to the atmosphere through evaporation. Evaporation removes water molecules while leaving nearly all of the dissolved material behind. The remaining brine becomes more concentrated. Once the water can no longer hold all of its dissolved salts, crystals begin to form. Sodium and chloride combine into halite, the mineral form of ordinary table salt. The surface crust often breaks into broad polygon shapes. Cooling, heating, moisture changes, and salt growth creates stress within the crust. Cracks spread until the surface is divided into many-sided plates. The white plain is the youngest visible layer of a much older story. Beneath it lie alternating beds of porous salt and fine clay-rich sediment. Those layers record former lakes that once filled much larger parts of the Altiplano. During wetter periods, deep lakes covered the basin. As the climate became drier, those lakes shrank into smaller bodies of water and salt flats. Scientists use the word paleolake for a lake that existed in the past and has since disappeared or changed greatly. Uyuni developed from several ancient lake systems rather than from one lake drying only once. Each return of water brought more dissolved material. Every later dry phase left another layer behind. During Bolivia's wet season, usually between December and April, rain may cover parts of the Sala with a shallow sheet of water. Only a few centimeters can be enough to transform the surface. Because the ground is so level, the water spreads widely and may remain calm. Clouds, mountains, and the sky then appear reflected below the horizon. The famous mirror effect lasts only while the water is present and smooth. For much of the year, travelers encounter a dry salt crust instead. The seasonal mirror is one temporary face of a landscape built through repeated drying. Farther southwest, across the Andes in northern Chile, Salar de Atacama covers roughly 2,100 square kilometers. Its surface is rougher than Uyuni's and includes ridges of halite, shallow lagoons, and exposed crust. Below the salt lies dense brine enriched with dissolved lithium, potassium, magnesium, and boron. Lithium is especially important in rechargeable batteries used in phones, computers, electric vehicles, and energy storage systems. At Salar de Atacama, companies pump underground brine into large evaporation ponds. Sunlight and extremely dry air remove much of the water. As the brine becomes more concentrated, different salts can be separated during several stages of processing. The method relies on the same natural rule that built the Salar. Water arrives carrying dissolved material. Then evaporation steadily removes the water. These basins show how a small chemical residue can accumulate into a landscape over thousands of years. After the shallow water retreats, salt crystals, fine clay, and loose sediment remain exposed beneath an open sky. Wind begins working across that surface, moving grains one short distance at a time. Across northern Chile, dry ground stretches between the Pacific coast and the high wall of the Andes. This is the Atacama, widely described as the driest non-polar desert on Earth. Some weather stations in its central core have recorded years with almost no measurable rain. Conditions vary across the region, however, because the Atacama extends for roughly 1,000 kilometers and includes coastal hills, salt basins, volcanic slopes, and high plateaus. Its dryness comes from several forces working together. Near 30 degrees south latitude, descending air from a large subtropical circulation pattern tends to warm and dry as it sinks. The Andes block much of the moisture arriving from the east. Closer to the Pacific, the Chilean coast range limits moist ocean air from moving inland. Offshore, the cold Humboldt Current cools the lower atmosphere and reduces the rising air needed to build rain clouds. The result is a landscape where loose sediment may remain exposed for long periods. NASA and other research groups have used parts of the Atacama to test equipment for Mars exploration. Its salt-rich soil, intense ultraviolet light, extreme dryness, and very low numbers of living cells in some areas create difficult conditions for drills and instruments designed to search for signs of life. Even in such a dry place, the ground keeps moving. A grain of sand may rest until a strong enough gust pushes it forward. Some grains roll along the surface. Others rise into short hops before falling again. Scientists call this hopping motion saltation. When one grain lands, it can strike several others and send them into motion. A dune migrates through millions of these small events. Sand is lifted from the side facing the wind and carried toward the crest. After crossing the top, grains tumble down the sheltered slope. The dune keeps a familiar curved or crescent shape, while its individual grains are continually rearranged. Under rare conditions, that moving sand can also create sound. Booming dunes are found in deserts across Africa, Asia, North America, and the Arabian Peninsula. A dry avalanche on a steep dune may produce a low tone that continues for several seconds. The sound can resemble a distant engine or a deep musical note. These dunes usually contain grains that are close in size, smooth from repeated contact, and extremely dry. As a thin sheet of sand slides down the slope, grains collide and move in a partly synchronized way. Their repeated motion sends vibrations through the flowing layer and the material beneath it. Researchers continue to study how grain motion, dune structure, and resonance each contribute to the final sound. The effect appears only after the sand crosses several thresholds involving dryness, grain shape, slope, and speed. A different threshold process left long tracks across racetrack playa in California's Death Valley. The playa is a flat lake bed surrounded by mountains. Stones that fell from nearby slopes somehow traveled across its clay surface, leaving trails that could extend for hundreds of meters. Some weighed hundreds of kilograms. For decades, people suggested powerful winds, unusually slippery mud, or thick sheets of ice. Direct observations finally captured the movement during the winter of 2013 into 2014. Rain had created a shallow temporary pond over part of the playa. Cold nights froze the surface into clear ice less than about 5 millimeters thick. Sunlight later warmed the ice and broke it into broad floating panels. Winds moving at roughly 3 to 5 meters per second pushed those panels across the water. The thin ice pressed gently against stones resting in softened mud. Several rocks began traveling at the same time, sometimes along parallel paths. Their speed remained slow, usually around 2 to 6 meters per minute. A person watching from far away might barely notice the movement. The stones could stop when the wind weakened, then move again, as another ice sheet arrived. After the water evaporated, their tracks remained visible across the dry surface. This event required rain, freezing temperatures, sunlight, thin ice, shallow water, and light wind to occur in the correct order. Most years did not provide the full sequence. The mystery lasted because the motion was both rare and quiet. Across deserts, wind can work for years before its effects become obvious. A dune shifts through countless hopping grains. A deep tone appears only when dry sand begins to slide together. Large stones move when a few millimeters of ice supply just enough force. Other landscapes receive energy through fractures beneath the surface, where heat, gas, burning fuel, and molten rock begin moving upward. Beneath the small town of Centralia, Pennsylvania, a fire has been moving through coal and abandoned mine passages since 1962. Centralia sits in a region rich in anthracite, a hard form of coal containing a high percentage of carbon. Mining created a network of underground tunnels, shafts, and exposed coal seams beneath the streets. In May of 1962, fire reached one of those coal deposits. The exact path from the original surface fire into the mine workings has been debated, though the underground result became clear. Coal continued burning below the town. An underground coal fire may advance through narrow cracks and forgotten tunnels. Fresh air enters through openings in the ground and supplies oxygen. Heat dries nearby coal until it can ignite. The burning zone then spreads into another part of the seam, sometimes far from the place where smoke first appeared. This made Centralia difficult to map and even harder to extinguish. The fire was hidden beneath layers of soil and rock. Digging out every burning section would have required locating an irregular network extending through unstable mine workings. Sealing one opening could redirect gas and heat toward another. At the surface, residents encountered smoke, sulfur-like smells, warm ground, and dangerous gases such as carbon monoxide. A sinkhole opened beneath a 12-year-old boy in 1981, dropping into hot, abandoned workings before he was pulled to safety. The event drew national attention to the instability below the town. During the 1980s, the United States government funded the relocation of most residents. Roads were closed, houses were removed, and Centralia's population fell from more than 1,000 people in the middle of the 20th century to only a few remaining residents. The heat beneath Centralia comes from burning fuel. Far away in Ethiopia's Afar region, heat reaches the surface through a different route. At Dallol, groundwater passes through fractures in crust that is being stretched and thinned. Hot rock below warms the water. The heated fluid moves through thick layers of salt left by ancient seas, dissolving minerals along the way. When the water returns to the surface, it may release steam, gas, and mineral-rich brine. Pools bubble beneath crusts of salt and sulfur compounds. The ground can feel alive with heat, though the energy comes from underground water circulating near volcanic activity. No coal seam is required. A third kind of fiery landscape appears at Kawah Ijen in eastern Java, Indonesia. The volcano releases gases containing sulfur compounds through openings called fumaroles. A fumarole is a crack or vent where hot volcanic gas escapes. Temperatures near these vents can rise above several hundred degrees Celsius. When sulfur-rich gas reaches the cooler air, part of it may condense into yellow liquid sulfur and then harden into bright deposits. Some of the gas also ignites. At night, the burning sulfur compounds produce electric blue flames that can travel along the ground. The site is often described as blue lava, though the visible blue comes from combustion. The rock melted beneath the volcano glows in the familiar orange and red range when exposed. Blue light belongs to the burning gas above it. The difference becomes especially clear at Erta Ale, another volcano in Ethiopia's Afar Depression. Erta Ale is a broad shield volcano, built mostly from fluid basaltic lava. Its slopes are gentle, because basalt can flow farther before cooling than thicker, stickier lava. The summit rises only several hundred meters above the surrounding depression, while the volcanic base spreads across many kilometers. Within its summit crater, Erta Ale has repeatedly held an exposed lava lake. Confirmed observations of persistent activity extend back through much of the 20th century, with especially well-documented lava lake behavior since the 1960s. A lava lake forms when molten rock remains connected to a deeper supply of magma. Hot material rises, cooler material sinks, and gases escape from the moving surface. Dark crust forms briefly before breaking apart and being pulled back into the glowing lake. Centralia, Dallol, Kawah Ijen, and Erta Ale may all produce heat, fumes, and colored ground. Their energy travels through separate systems. Coal burns through old mine passages. Heated water carries minerals through salt. Sulfur-rich gas ignites after leaving a volcanic vent. Magma reaches the open surface as liquid rock. In the Afar region, that magma is rising where Earth's crust is slowly pulling apart. When the same process reaches shallow seawater, enough volcanic material can gather above the waves to create an entirely new island. South of Iceland, the mid-Atlantic ridge passes beneath the ocean. Along this ridge, two tectonic plates are slowly moving apart. Magma rises through the opening and cools into new ocean crust. Most of that activity remains hidden below the waves. On the morning of November 14, 1963, people aboard a fishing vessel noticed a dark column rising from the sea, about 32 kilometers from Iceland's southern coast. At first, the smoke-like shape could have been mistaken for a burning ship. Ash soon began falling onto the vessel, and the water ahead was disturbed by repeated explosions. The eruption had probably begun several days earlier on the seafloor. Once the growing volcanic cone reached shallow water, the activity became visible above the surface. Hot basaltic magma met cold seawater. The water heated almost instantly and expanded toward steam. That sudden expansion shattered the magma into ash, glassy fragments, and larger pieces of volcanic rock. Scientists call this kind of activity phreatomagmatic eruption, meaning an eruption driven by direct contact between magma and water. Each explosion threw material upward before it fell back into the sea or landed around the vent. Ash and rock slowly gathered into a dark island. Waves struck the new shoreline from the moment it appeared. The earliest deposits were loose and easily broken apart. Some portions collapsed into the water almost as quickly as the eruption rebuilt them. By the end of November, the island had grown to several hundred meters across. It was named Surtsey after Surtur, a fire figure from Norse mythology. The eruption continued through a series of vents from 1963 until June of 1967. Its behavior changed as the island grew. Once the vents became separated from direct contact with seawater, the explosions weakened. Lava began flowing more steadily across the surface. Basalt spread over the loose ash and cooled into harder rock. These lava layers protected parts of Surtsey from the North Atlantic waves. Without them, much more of the young island might have disappeared soon after the eruption ended. The type of material mattered as much as the amount produced. Soft ash cliffs retreated quickly. Solid lava resisted erosion and formed a tougher central core. Scientists began monitoring Surtsey in 1964, while eruptions were still adding land. The island was protected by Icelandic law, and visits were tightly controlled. Researchers wanted to observe how life reaches fresh land without farms, gardens, roads, or permanent settlements affecting the process. This gradual arrival of life on a bare surface is called primary succession. At first, Surtsey contained volcanic rock, ash, salt spray, and little organic soil. Bacteria and fungi arrived early. Some traveled in the air or ocean. Others came attached to drifting wood, seaweed, birds, or insects. Seeds could float across the water, blow through the air, or pass through a bird's digestive system before landing on the island. The first vascular plant was recorded in 1965. Vascular plants contain internal tubes that carry water and nutrients through their stems, roots, and leaves. Sea rocket, a plant that tolerates salty coastal conditions, was among the early colonists. Many seeds arrived without surviving for long. Young plants face strong wind, cold winters, salt spray, loose ground, and limited nutrients. Birds gradually changed those conditions. Gulls began nesting in larger numbers during the 1980s. Their droppings added nitrogen and other nutrients to the soil. Feathers, eggshells, food remains, and dead plant material also increased the amount of organic matter. Denser vegetation developed around the nesting colony. By 2004, researchers had recorded about 60 species of vascular plants on Surtsey, although some appeared only briefly. Insects arrived through flight, drifting air, ocean debris, and transport by birds. Spiders could travel on strands of silk carried by the wind. Seals rested along the shore, while algae and marine animals occupied the underwater rock around the island. Every arrival depended on a route, suitable conditions, and enough luck for reproduction to begin. Meanwhile, the ocean continued removing the land beneath the growing ecosystem. Waves have already carried away roughly half of Surtsey's largest recorded area. Loose deposits disappeared fastest, while cooled lava slowed the retreat. Future erosion is expected to leave a smaller, harder remnant that may survive far longer than the original ash coastline. Surtsey therefore records several changes at once. A volcano constructed the ground during 4 years of eruption. Living organisms began altering it before the eruption had finished. The sea has been reducing its size ever since. This entire sequence has unfolded within the lifetime of people who remember the morning when smoke first appeared above open water. Surtsey shows how isolation begins. On older islands, the same separation can continue for millions of years, giving plants and animals enough time to follow evolutionary paths found nowhere else. A seed reaching a new island may survive only a season. If its descendants remain separated for thousands of generations, the result can become a species found nowhere else. The Socotra archipelago lies near the mouth of the Gulf of Aden, between the Arabian Peninsula and the Horn of Africa. Its largest island rises from dry coastal plains into limestone plateaus and mountains more than 1,500 meters high. Seasonal monsoon winds strike the archipelago from different directions during the year. Some slopes receive mist and cloud. Other areas remain hot, rocky, and extremely dry. These differences create many habitats within a relatively small area. Socotra has never been completely sealed from the outside. Seeds have arrived in seawater. Birds have crossed from nearby continents, and flying insects have traveled with the wind. The crossings are uncommon enough that many populations remain separated after they arrived. Over long periods, that separation allowed them to change along their own paths. Scientists have recorded about 825 plant species on Socotra. 307 are endemic. An endemic species occurs naturally in one limited place and nowhere else. This means roughly 37% of Socotra's known plants are unique to the archipelago. The pattern becomes even stronger among animals that have difficulty crossing seawater. Of the 34 recorded reptile species, about 90% are endemic. Socotra also contains 96 known species of land snail, with roughly 95% found nowhere else. A snail may spend its whole life within a small patch of rock, soil, and vegetation. Ocean water forms an enormous barrier for an animal that moves only a short distance each day. One of Socotra's best-known plants is the dragon's blood tree, Dracæna cinnabari. Its branches divide again and again near the top, forming a broad crown shaped like an open umbrella. The dense canopy shades the ground beneath it and reduces direct heating around the roots. Leaves near the outer surface can intercept mist and droplets carried sideways by the wind. Some of that moisture reaches the trunk and soil below. The crown also limits overlap between neighboring trees as they compete for light and water. Several pressures helped shape this architecture, rather than one single purpose explaining the entire form. The tree produces a dark red resin that has been collected for centuries. People used it as a pigment, varnish, incense ingredient, and traditional medicine. Its color inspired the name dragon's blood. The evolutionary process behind Socotra's unusual life begins when a small founding population arrives. That group may carry only part of the genetic variation present in the larger population it came from. New mutations appear as generations pass. Local heat, rainfall, food, predators, and disease affect which individuals leave more offspring. Limited gene flow means that few outsiders arrive to mix their genes with the isolated group. Chance also plays an important role. Genetic drift is the gradual change in a population caused by random differences in which individuals reproduce. Its effects can be especially strong in small island populations. A storm may remove several animals from one valley. A few surviving seeds may produce most of the plants in the following generation. Traits can become common through chance, even when they offer no special advantage. Natural selection and random drift work together across long stretches of time. This helps explain why every unusual island feature should not be treated as a perfect solution designed for one task. Isolation also concentrates risk. A reptile confined to one plateau may have no second population elsewhere. An introduced rat, cat, insect, or plant disease could spread through much of its global range. Heavy grazing by livestock can prevent young dragon's blood trees from replacing older ones. Severe cyclones have damaged forests, while changing rainfall and rising temperatures may reduce the cool, misty conditions some species depend on. Large protected zones now cover much of Socotra's land and important parts of the surrounding sea. Protection can limit development and reduce direct habitat loss. Though storms, invasive species, grazing, and climate shifts remain difficult to control. Socotra's biological richness grew because distance slowed the movement of genes and organisms. A different kind of isolation forms where water dissolves the ground itself, leaving forests enclosed at the bottoms of immense vertical walls. In southern China, some isolated habitats lie far below the surrounding hills. They are enclosed by cliffs rather than ocean. The Chinese word tiankeng is often translated as heavenly pit. It refers to an exceptionally large, steep-sided sinkhole formed in thick layers of carbonate rock, especially limestone. One of the best-known groups lies near Lai County in Guangxi. The Dashui cluster contains 35 large collapsed depressions spread across a landscape of wooded ridges and deep underground drainage. Their formation begins with ordinary rain. As raindrops move through the atmosphere, they absorb a small amount of carbon dioxide. Far more enters the water after it reaches the ground and passes through soil filled with plant roots, fungi, and decaying organic material. The carbon dioxide reacts with water and produces weak carbonic acid. This mild acid is similar to the acidity found in sparkling water. Limestone consists mainly of calcium carbonate, which slowly dissolves when acidic water reaches it. The process begins along natural weaknesses in the rock. Joints are cracks where the limestone has split. Bedding planes are boundaries between layers deposited at different times. Faults form where sections of rock have moved against one another. Water enters these narrow openings and removes tiny amounts of mineral with each passage. A crack may gradually widen enough to carry a steady underground stream. Continued dissolution creates channels, chambers, and cave systems beneath the hills. Flowing water also carries loose sediment away. This matters because dissolved rock and broken material must leave the growing space. An underground river can transport both through passages that may extend for many kilometers. The land above can remain intact while the hollow beneath it becomes wider. Eventually, the roof may lose enough support to fracture. Blocks of limestone fall into the chamber and are broken down or carried away by water. Repeated collapse works upward until the hidden space opens to the sky. A tiankeng is the enormous surface opening left by that long underground history. The Dashaway Tiankeng reaches approximately 613 meters from its rim to its deepest floor. Its opening measures more than 600 meters across in one direction. Standing near the edge, a person would see forest canopy far below, with sections of exposed limestone wall descending between ledges. The scale is large enough that clouds, mist, and shadow can hide portions of the floor. Nearby depressions belong to the same wider karst system. Karst is the name used for terrain shaped by the dissolving of soluble rock. Underground rivers connect several caves and collapsed dolines in the region. A doline is another word for a sinkhole, usually smaller than the giant features classified as tiankengs. The floor of a deep sinkhole receives different amounts of sunlight through the day. Direct wind is reduced by the surrounding walls. Cool air can settle in low areas, while moisture remains longer beneath dense vegetation. Rainwater collects along ledges and enters cracks before reaching the underground river below. These conditions create a sheltered microclimate. A microclimate is the set of local temperature, light, wind, and moisture conditions found within a small area. Exploration teams have reported trees around 40 meters tall in some Chinese sinkholes. Ferns, mosses, and shade-tolerant plants occupy damp ground beneath the canopy. Cliff faces provide narrow habitats for plants rooted in cracks. Cave entrances around the floor may shelter bats, insects, and animals adapted to limited light. Biological separation varies from one pit to another. Some floors can be reached through cave passages or steep routes used by local people. Animals may climb, fly, or enter with underground streams. Nearby human activity can also affect water quality and vegetation. Even with those connections, the vertical walls reduce movement enough to create unusual pockets of habitat. The forest at the bottom grows on material that once supported a cave roof. Its soil contains fallen leaves, weathered limestone, and sediment delivered by water. Roots enter cracks that the same weak acid continues to enlarge. The sinkhole therefore remains an active part of the underground drainage system. Water still passes beneath the trees and disappears into openings along the floor. Following that river away from the daylight leads into chambers where the boundaries between cave and landscape begin to blur. The underground river continues beneath the limestone, following cracks that have widened over immense spans of time. In central Vietnam, this hidden drainage passes through Phong Nha Ke Bang National Park, a region filled with caves, sinkholes, steep forested hills, and underground streams. One entrance remained little known until a local man named Ho Kan encountered it while traveling through the forest. He remembered a strong flow of air and the sound of water coming from the darkness. Years later, he helped guide a British-Vietnamese expedition back to the site. In 2009, the team formally surveyed the cave now known as Son Dung. Its Vietnamese name means mountain river cave. The name fits a passage shaped around an active underground river that still moves through parts of the system. Son Dung contains the largest documented cave passage measured by its great width, height, and continuous size. The cave extends for several kilometers. Major chambers rise close to 200 meters from floor to ceiling. Some sections measure more than 100 meters across, while estimates place the cave's internal volume in the tens of millions of cubic meters. Those measurements describe an enclosed space large enough for distances to become difficult to judge. A headlamp may illuminate nearby rock while the far wall remains hidden. Sound can travel through the chamber, reflect from distant surfaces, and return after a noticeable delay. The scale developed gradually through the movement of water. Rain falling on the forest above absorbed carbon dioxide from the soil and became mildly acidic. The water entered fractures in the limestone and dissolved small amounts of calcium carbonate. Streams also carried sand, gravel, and broken rock. Those materials scraped against the floor and walls, adding physical erosion to the chemical dissolving of the stone. The river followed weaker zones within the limestone rather than carving one simple straight tunnel. Faults, joints, and boundaries between rock layers guided its route. As the region changed, underground drainage also shifted. A passage might carry a strong river for thousands of years, then become partly abandoned when water found a lower route. Sondong belongs to a much wider landscape of connected cave systems, including Hang En and other passages within Fongnakebang. The cave did not appear during one sudden collapse. Water enlarged it in stages, while sections of roof weakened under their own weight. Some eventually fell. 2 enormous roof collapses created openings called dolines. Sunlight enters through these gaps and reaches piles of broken limestone and sediment below. Rain falls directly onto parts of the cave floor. Seeds arrive on the wind, in animal droppings, or attached to material washed through the opening. Vegetation grows where enough light and soil collect. One doline supports dense plants and trees within the cave. The second contains another green interior zone surrounded by high rock walls. These patches are linked to the surface, though their position below the rim changes the amount of wind, sunlight, and moisture they receive. Insects, birds, and other small animals can enter through the openings. Cave-adapted organisms occupy darker areas farther from daylight. The river supplies constant moisture, while dripping water continues depositing minerals along quieter sections of the passage. Sondong is sometimes described as having its own weather. The phrase refers to real local conditions, though the cave does not contain a complete weather system separate from the atmosphere outside. Warm, humid air can enter through one opening, while cooler air remains deeper inside. Pressure differences push air through the long passage. Water from the river and wet rock adds moisture. When humid air cools against colder surfaces, some water vapor condenses into tiny droplets. Mist may gather beneath the ceiling or drift through a doline. Strong air movement can also develop where the cave connects openings at different elevations. Temperature differences between the forest and the cave help drive this flow. During certain conditions, low cloud-like mist forms within the chamber, softening the outlines of cliffs and vegetation. The effect comes from moisture, cooling, and moving air working together inside an unusually large enclosed space. Sondong contains an active river, collapsed ceilings, interior forests, mist, and passages extending beyond easy view. Each feature grew from the same long interaction between water and limestone. Flowing water removed enough rock to create the chamber, In other underground rooms, mineral-rich water remained nearly still, allowing dissolved material to gather into crystals larger than a person. Water moving through Sondung carried dissolved rock away. Far beneath northern Mexico, another body of water remained almost still for so long that minerals had time to build structures larger than people. The Nika mine lies in the state of Chihuahua. Mining tunnels there descend through limestone above a deep source of volcanic heat. In the year 2000, workers opened a chamber roughly 300 meters below the surface and found enormous clear crystals crossing the room. Some stretched from the floor toward the ceiling like pale beams. The chamber became known as the Cave of the Crystals. Its air was close to 50 degrees Celsius, with humidity near full saturation. Under those conditions, sweat could no longer cool the body effectively because the surrounding air already held so much moisture. Researchers wore cooling suits and breathing equipment, and visits were kept brief. The crystals are gypsum, a mineral made from calcium sulfate combined with water inside its structure. Their formation began with a related mineral called anhydrite. Anhydrite contains calcium sulfate but lacks the water held within gypsum. Deep underground, heat from nearby magma kept the chamber water warm enough for anhydrite to remain stable in the surrounding rock. Over time, the water cooled through a narrow temperature range. Anhydrite began dissolving. Calcium and sulfate entered the water, while gypsum became the more stable solid. Tiny amounts of gypsum then joined the surfaces of existing crystals. This growth happened extremely slowly. The water remained close to chemical balance, meaning it contained only slightly more dissolved material than gypsum could hold. That slight excess allowed crystals to grow without causing minerals to suddenly coat every surface. New crystal beginnings, called nuclei, formed only rarely. With few crystals competing for the available material, the ones that had already started could continue growing for hundreds of thousands of years. Some reached approximately 11 to 12 meters in length. Several were close to 1 meter thick. Their great size required warm, mineral-rich water, an open chamber, and an unusually stable temperature. A faster change could have produced many smaller crystals. Cooling too far would have ended the special conditions. The chamber remained flooded during most of its crystal-growing history. Mining pumps later lowered the underground water and exposed the crystals to air. Without the flooded environment, their long period of growth stopped. North of Nika, across the border in New Mexico, Carlsbad Caverns records another kind of water chemistry. Many limestone caves begin when rainwater absorbs carbon dioxide from soil and forms weak carbonic acid. That water moves downward through cracks and gradually dissolves the rock. Carlsbad's largest chambers were shaped mainly by sulfuric acid rising from below. Deep groundwater carried hydrogen sulfide from deposits associated with oil and gas in the surrounding region. When this gas-rich water reached areas containing oxygen, chemical reactions produced sulfuric acid. The acid attacked the limestone, which consists mostly of calcium carbonate. Large amounts of rock dissolved, helping form broad rooms and passages. Important stages of this cave development took place roughly 4 to 6 million years ago, although the wider geological history extends much farther back. Sulfuric acid also reacted with calcium from the limestone and produced gypsum. Thick gypsum deposits remain on cave walls and floors as evidence of the older chemistry. Nearby Lechugilia Cave contains large areas of gypsum and unusual mineral formations created through related processes. Some appear as delicate white hairs, crusts, or branching shapes. These deposits preserve clues about the gases, water, and rock that once met underground. After the corrosive groundwater level dropped, a different phase began. Rainwater entered from above and moved through soil and limestone. Each drop carried a small amount of dissolved calcium carbonate. When the water reached an open cave and released carbon dioxide into the air, part of that mineral became solid again. Deposits hanging from ceilings formed stalactites. Material building upward from the floor formed stalagmites. The large chambers came first through dissolution. Many familiar cave decorations arrived later, through slow mineral deposition. Nika and Carlsbad therefore preserve opposite movements within water. At Nika, dissolved material gathered into crystals under steady warm conditions. At Carlsbad, acidic water removed limestone, before later drips returned small amounts of mineral to the empty space. A cave can preserve the chemistry of water long after the water itself has moved on. Deep lakes hold even longer records, because some basins have remained filled while mountains rose, climates shifted, and new species evolved around their shores. Far below the surface of southeastern Siberia, a basin has remained filled with water for roughly 25 million years. Lake Baikal survives because the land beneath it is still changing. Most lakes are temporary on a geological clock. Rivers deliver clay, sand, dead plants, and broken rock until a basin gradually fills. Some lakes lose their outlets and shrink. Others drain when rivers cut new paths through surrounding land. Glaciers can also erase or reshape them as climates shift. Baikal occupies a different kind of setting. It lies inside an active continental rift, where sections of Earth's crust are slowly being pulled apart. As the crust stretches, large blocks of rock sink between faults. A fault is a break in the crust where rock has moved. This downward movement creates new space for water and sediment. Geologists call that space accommodation. The basin can keep deepening even while rivers carry material into it. This balance has allowed Baikal to persist far longer than an ordinary lake. The rift extends through southeastern Siberia, north of Mongolia. Lake Baikal itself is more than 600 kilometers long. Its narrow, curved shape follows the sunken zone between major faults. Modern measurements place its deepest water near 1,642 meters. Some broad descriptions round that depth to about 1,700 meters. At its deepest point, the lake floor lies more than 1 kilometer below sea level, because the water surface already sits hundreds of meters above the ocean. Baikal's enormous volume comes from its length, width, and depth working together. It contains close to 1/5 of the world's unfrozen surface freshwater. That figure refers to liquid freshwater held in lakes and other open surface bodies. It does not include all freshwater on Earth. Much larger amounts remain locked inside glaciers and ice sheets, or stored underground in rock and sediment. Even with that distinction, Baikal holds an extraordinary reserve. More than 300 rivers and streams flow toward the lake. Only one major river, the Angara, carries water away. The lake freezes across much of its surface during the Siberian winter. Clear ice can grow more than a meter thick in some areas, while the deep water below remains liquid. Baikal's age has given living populations a long period of separation. Thousands of species and subspecies have been recorded in and around the lake. A large share occur naturally nowhere else. This high endemism developed because organisms remained within a deep, varied environment containing rocky shores, open water, river mouths, and dark bottom habitats. Among the best-known residents is the Baikal seal. It is the only seal species that lives exclusively in fresh water. Adults spend much of their lives feeding on fish in the lake and resting or breeding on winter ice. How the ancestors of these seals first reached Baikal remains debated. Possible routes involve ancient river connections and movement through northern waterways during colder periods. Once established, the population became isolated far from the sea. Small crustaceans called amphipods provide another example. Many are only a few centimeters long, though the lake contains a wide range of forms. They crawl across rocks, consume organic material, prey on smaller animals, and help recycle nutrients. Hundreds of amphipod species have evolved within Baikal. Freshwater sponges also grow across parts of the lake floor. Some form branching green shapes because algae live inside their tissues. The algae use sunlight near shallower areas, while the sponge filters tiny particles from the water. Farther down, life continues under colder temperatures and much greater pressure. The lake floor also keeps a physical record of the world above it. Year after year, fine particles settle through the water. Wind carries dust and pollen from forests and grasslands. Rivers deliver mineral grains worn from surrounding mountains. Microscopic organisms leave shells or other remains after they die. Chemical changes in the sediment can record shifts in oxygen, temperature, vegetation, and rainfall. These materials accumulate in layers that researchers recover using long drilling tubes called sediment cores. A core preserves older deposits beneath younger ones. Pollen can show which plants grew nearby during an earlier climate. Mineral grains may reveal changes in erosion or river flow. Biological remains can track periods when the lake held different temperatures or nutrient levels. Baikal therefore stores time in two connected ways. Its living species carry the results of long isolation. Its sediment holds evidence of climates and landscapes that have already disappeared. The same depth that protects this archive also creates immense pressure near the lake floor. In another deep basin, pressure allowed carbon dioxide to remain dissolved until a quiet volcanic lake stored far more gas than its surface could reveal. Near the border between Cameroon and Nigeria, Lake Nyos rests inside a volcanic crater surrounded by green hills. Its surface can appear calm, with dark water reflecting the slopes around it. The lake reaches more than 200 meters deep. Far below the surface, carbon dioxide enters the water from geological sources connected to the volcanic region. The gas rises through cracks in the rock and dissolves into the cold water near the lake floor. Pressure allows that deep water to hold much more carbon dioxide than water near the surface. A sealed bottle of sparkling water offers a simple comparison. Inside the closed bottle, pressure keeps much of the gas dissolved. Opening the cap lowers the pressure, allowing bubbles to appear. Lake Nyos followed the same basic physical rule on a far larger and more complicated scale. Its water formed stable layers. Warm surface water remained above colder, denser water. Seasonal weather did not mix the lake completely from top to bottom. This allowed the deepest layer to remain isolated for long periods. Carbon dioxide continued entering and gradually accumulated there. The gas could remain nearly invisible while dissolved. Deep water may look clear even while holding a large amount of carbon dioxide. Trouble begins when gas-rich water starts moving upward. Pressure decreases as the water rises. Dissolved carbon dioxide then forms bubbles. Those bubbles reduce the density of the surrounding water, making the mixture more buoyant. Faster upward movement causes another drop in pressure, which releases still more gas. Scientists describe this kind of accelerating cycle as positive feedback. A small upward movement can strengthen itself until a much larger flow develops. On August 21st, 1986, Lake Nyos released a huge amount of carbon dioxide. The exact trigger remains uncertain. A landslide, cooling rainwater, strong wind, or gradual instability within the deep layer may have helped start the upward movement. Once the release began, gas-rich water rose quickly and carbon dioxide escaped at the surface. The event is called a limnic eruption. The word limnic refers to a lake. During this type of eruption, dissolved gas leaves the water rapidly. No lava erupts from the lake. Carbon dioxide has no color and little smell, which made the moving cloud difficult to detect. It is also denser than ordinary air. After leaving the lake, the gas flowed downhill through low ground and followed valleys and drainage channels. Air containing a very high concentration of carbon dioxide holds too little oxygen for people and animals to breathe safely. Approximately 1,700 people died in nearby communities. Reports also recorded the loss of roughly 3,000 to 3,500 cattle and other livestock. The affected area extended many kilometers from the lake. Investigators arriving afterward found that the lake itself had changed color near the surface. Deep water brought upward during the event contained iron. Once exposed to oxygen, that iron formed reddish compounds, creating a temporary color change similar in basic chemistry to rust. The disaster showed that the dangerous material could continue accumulating unless the deep water was managed. Researchers first tested ways to release the gas in a controlled manner. A permanent degassing pipe began operating in 2001. The pipe reaches into the deep, carbon dioxide-rich water. Water is initially pumped upward through it. As pressure falls inside the pipe, bubbles begin forming. The mixture of water and gas becomes lighter than the surrounding lake water, so it continues rising without constant pumping. A tall fountain then emerges above the surface. Some self-driven fountains at Lake Nyos have reached roughly 45 meters. Additional pipes were later installed to increase the rate of controlled gas removal. Each fountain releases carbon dioxide gradually into open air, rather than allowing it to remain concentrated in the lake's deepest layer. Scientists continue measuring gas levels, water temperature, and the stability of the lake. The crater walls and a natural dam at one end have also required attention, because changes in water level could affect nearby valleys. Lake Nyos became understandable through pressure, density, and dissolved gas. Its quiet surface concealed a deep layer that behaved differently from the water above. Far to the south, beneath Antarctic ice, another hidden liquid remains mobile through a separate physical rule. There, salt lowers the freezing point enough for water to persist in a landscape dominated by ice. Along the coast of Antarctica, west of McMurdo Sound, a series of broad valleys cuts through mountains of dark rock. They are known as the McMurdo Dry Valleys. Together, they form one of the largest ice-free regions on the continent. The surrounding landscape contains glaciers, frozen lakes, bare gravel, and steep valley walls. Very little snow falls there. Mountains block some of the ice flowing outward from the Antarctic interior, leaving sections of ground exposed. Strong winds also descend from the high ice sheet toward the coast. These are called katabatic winds. The word describes cold, dense air flowing downhill under the pull of gravity. As the air drops to lower elevations, it can warm slightly and become even drier. Wind speeds in the dry valleys can rise high enough to sweep away loose snow and increase evaporation from exposed surfaces. The ground may therefore remain bare even while glaciers occupy the valleys around it. One of those glaciers is Taylor Glacier. At its end, a dark red stain spreads across pale ice and frozen ground. The feature is known as blood falls because of its color. Its source is a concentrated brine moving through and beneath the glacier. Brine is water containing far more dissolved salt than ordinary seawater. The liquid is thought to include ancient water that became trapped as glaciers advanced across the region. Fresh water normally freezes at 0 degrees Celsius. Dissolved salt interferes with the formation of an orderly ice crystal, lowering the temperature at which freezing occurs. This process is called freezing point depression. The same principle is used when salt is spread on an icy road. Taylor Glacier's brine contains enough salt to remain liquid at temperatures that would freeze fresh water solid. Pressure beneath the ice also affects the system. As some water freezes, the remaining liquid becomes even saltier, because most of the dissolved material is pushed out of the growing ice crystals. Freezing releases a small amount of heat into the surroundings as well. Together, salinity, pressure, and heat exchange allow narrow pockets and channels of liquid brine to survive inside a largely frozen environment. The liquid moves slowly through cracks and connected spaces within the glacial system. It carries iron collected through contact with rock and sediment beneath the ice. Much of that iron remains dissolved while the brine is sealed away from free oxygen. Near the glacier's edge, the liquid reaches the surface. Oxygen from the air then reacts with the iron. The process is oxidation, the same broad chemical change that produces rust on exposed metal. Iron compounds form reddish particles and stains across the ice. The color becomes especially noticeable against the surrounding white glacier. Blood falls contains more than salt and iron. Samples of the brine have revealed microorganisms adapted to cold temperatures, darkness, high salinity, and very little available oxygen. Sunlight cannot reach the hidden water beneath the glacier. The microbes depend on chemical reactions involving materials in the brine and surrounding rock. Some take part in sulfur cycling, changing sulfur compounds from one chemical form into another. Iron also moves through different forms as microbes and minerals interact, These reactions provide usable energy in a place where photosynthesis cannot occur. The community does not show that life can survive under every extreme condition. Its existence depends on a specific balance of liquid water, chemical energy, salts, nutrients, and temperatures that remain within biological limits. Other parts of the McMurdo Dry Valleys contain lakes covered by ice for much or all of the year. The ice reduces wind-driven mixing and shields the water below from the coldest surface conditions. During the brief Antarctic summer, sunlight passes through thinner sections of ice. Meltwater from nearby glaciers may feed small streams for a few weeks. Some lakes remain liquid beneath their frozen covers and support algae, bacteria, and other microscopic organisms. Bloodfalls gathers several processes into one narrow outflow. Iron creates the visible color after meeting oxygen. Salt keeps water liquid below its usual freezing point. Glacial ice isolates the brine for long periods. Microorganisms obtain energy through chemical reactions in darkness. A landscape that appears dry and frozen still contains movement beneath its surface. The same mountains and winds that help keep these valleys exposed also shape the atmosphere above them. In other parts of the world, surrounding terrain concentrates moisture and rising air, creating places where storms return with unusual regularity. That influence becomes especially clear after sunset over northwestern Venezuela. Lake Maracaibo lies within a broad lowland basin surrounded by mountains on several sides. Warm water, humid tropical air, and nearby wetlands supply abundant moisture. During the day, sunlight heats the land and lower atmosphere. After dark, cooler, denser air begins descending from the surrounding slopes. Mountain winds and valley winds then move toward the low basin around the lake. As these streams of air meet, they push warm, moist air upward. Rising air expands and cools. Water vapor condenses into cloud droplets, while continued lifting helps tall thunderclouds develop. This repeated nighttime pattern has made the Lake Maracaibo region one of the most active lightning areas on Earth. A major satellite study using the Lightning Imaging Sensor identified it as the leading global lightning hotspot. The instrument recorded brief flashes of light from thunderstorms over many years. Across the hotspot area, the average reached roughly 233 lightning flashes per square kilometer each year. One NASA account described nocturnal thunderstorms occurring on about 297 nights per year. Those figures are long-term averages calculated across a particular region and observation period. They do not mean that every point on the lake receives lightning every night. Storm numbers shift with seasons, wind patterns, moisture, and larger changes in tropical weather. The concentration remains extraordinary because the surrounding geography helps rebuild similar conditions again and again. A deep basin produces a different atmospheric extreme in eastern California. Death Valley lies between several mountain ranges in the dry interior of North America. Furnace Creek sits below sea level, while high ridges rise on both sides of the valley. Moist air traveling inland from the Pacific must climb over mountain slopes. As the air rises, it cools and releases rain or snow on the western sides of the ranges. The air then descends toward Death Valley with much of its moisture already removed. Descending air becomes warmer as pressure increases at lower elevations. This rain shadow effect helps create one of the driest places in North America. Furnace Creek receives less than about 5 centimeters of rain during an average year. Clear skies allow strong sunlight to reach the ground for long periods. Dark rock, gravel, and bare soil absorb that energy and heat the air directly above them. Sparse plant cover provides little shade or cooling through the release of water from leaves. The deep valley also allows heated air to remain close to the surface. Warm air rising along the valley walls may cool slightly, descend again, and return to the basin floor. This circulation can repeatedly pass air through a very hot environment. On July 10, 1913, a weather station at Furnace Creek recorded 56.7 degrees Celsius. The World Meteorological Organization continues to recognize this as the highest official air temperature measured at Earth's surface. Researchers have debated the reliability of some early 20th century extreme readings, including the quality of instruments and local observing conditions. The official record remains in place, while modern temperature studies continue to examine how older measurements were made. Far across the Pacific, geography shapes clouds into long rolling bands over northern Australia. Near the Gulf of Carpentaria, formations known as morning glory clouds sometimes appear as low tubes stretching across the sky. Some extend for hundreds of kilometers. They are most often observed during the dry season transition around September and October, though their exact timing and size vary. The Gulf, the Cape York Peninsula, and surrounding land surfaces heat and cool at different rates. Sea breezes move inland from opposing coastlines during the day. When these air masses meet, they can lift a stable layer of air and create a traveling atmospheric wave. The motion resembles a wave moving through water. Air rises along the front of the wave, expands, and cools until water vapor condenses into cloud. Behind the crest, the air sinks and warms, causing the cloud droplets to evaporate. The visible cloud therefore forms continuously along one side and fades along the other. Its rolling appearance follows the movement of air through the wave. The landscape below has organized the atmosphere into a moving shape that may travel for hours. Lake Maracaibo gathers moisture and nighttime winds into repeated storms. Death Valley concentrates heat within a deep, dry basin. Northern Australia turns sea breezes and stable air into a cloud hundreds of kilometers long. These patterns return because the mountains, coastlines, and lowlands remain in place. Some strange landscapes are far less dependable, appearing only when rain, temperature, wind, and timing briefly align. At Salar de Uyuni, the famous mirror appears only during a narrow part of the year. Rain falling across the Bolivian Altiplano spreads over sections of the salt crust during the wet season. The water may be only a few centimeters deep. Depth matters less than the unusual flatness of the surface beneath it. When wind remains light, the shallow sheet becomes smooth enough to reflect clouds and distant mountains. The horizon can seem to disappear because the sky above and the reflected sky below meet along one faint line. A stronger breeze breaks the surface into ripples. Continued evaporation exposes the white salt again. The location stays in place while its most recognizable form appears only for a limited time. Racetrack Playa in Death Valley follows an even narrower schedule. its stones may remain motionless for years. Rain must first create a shallow pond across part of the dry lake bed. Temperatures then need to fall low enough for a thin layer of ice to form during the night. Daylight weakens and breaks that ice into broad floating sheets. A gentle wind can push the sheets against stones resting in soft mud. The observed ice was only a few millimeters thick, yet it covered enough area to transfer force across the water. Stones then moved at roughly 2 to 6 meters per minute. The motion could last only a short time before the wind changed, the ice broke apart, or the water became too shallow. Most visitors arrive after the event. They see tracks pressed into dried mud, while the water and ice that produced them are already gone. Death Valley created another short-lived landscape after unusually heavy storms in 2023 and early 2024. Rainwater drained from surrounding mountains into Badwater Basin, the lowest area in North America. A broad, temporary lake formed across the salt and mud. People often called it Lake Manly, borrowing the name of a much larger prehistoric lake that occupied the basin during wetter periods of the Ice Age. The modern lake was shallow, though its surface extended across several kilometers. NASA's Surface Water and Ocean Topography satellite observed it during February and March of 2024. The mission is commonly called SWOT. It uses radar to measure the height and spread of water across lakes, rivers, reservoirs, and the ocean. Researchers compared the measured water surface elevation with maps of the basin floor. The difference between those two heights gave an estimate of depth. During part of February, deeper areas held water roughly 1 meter deep. Several weeks later, much of the lake had fallen below about half a meter. Evaporation removed water under the valley's dry air and strong sunlight. Some water also soaked into sediment or shifted toward the lowest parts of the basin. Wind changed the lake's outline by pushing the shallow water from one side toward another. A view from the shore on one day could therefore look different only a short time later. Temporary landscapes can also last for decades. Surtsey remains above the ocean more than 60 years after its eruption began, yet its coastline has never stopped changing. The island reached its greatest area near the end of the 1960s. North Atlantic waves then began removing loose ash and fragmented volcanic material. Cliffs retreated as storms struck them. Sediment traveled along the shore and collected in temporary beaches that later shifted again. Hard basaltic lava has resisted erosion more successfully and protects part of the island's central core. Surtsey has already lost a large share of its original area. Its remaining form will continue changing as softer deposits disappear and the most durable rock survives. These places occupy very different spans of time. Ice may push a stone during a single winter morning. A shallow lake can remain for several months before heat and dry air remove it. An island may shrink gradually across many human generations. Their strange appearance belongs to one stage within a longer cycle of rainfall, freezing, erosion, or evaporation. A photograph captures the stage without showing the conditions that formed it, or the changes already underway. Satellites can now follow temporary water across a desert from hundreds of kilometers above Earth. Far below that view, the permanent ocean hides mountain ranges, trenches, and saltwater pools beneath several kilometers of dark water. Far above Death Valley, a satellite can measure the height of a temporary lake by sending radar toward its surface. The ocean floor presents a much harder problem. Satellites can detect broad changes in sea surface height, caused by the gravity of underwater features. A large seamount pulls slightly more water toward it, creating a small rise at the surface above. These measurements reveal the general shape of the hidden terrain. Detailed maps require research vessels to send sound through the water. The seafloor is far from flat. Continental shelves extend outward from coastlines beneath relatively shallow water. Their edges descend along steeper continental slopes toward the deep ocean. Submarine canyons cut through some of these slopes, carrying sediment into deeper basins. Beyond them lie abyssal plains, broad regions covered by fine sediment several kilometers below the surface. Long mid-ocean ridges rise where tectonic plates separate and new crust forms. Individual underwater volcanoes called seamounts may climb thousands of meters from the surrounding floor without reaching the surface. Fracture zones form long scars where sections of crust moved past one another. The greatest depths occur in trenches, where one tectonic plate bends downward beneath another. Challenger Deep lies within the southern part of the Mariana Trench in the western Pacific Ocean. Modern measurements place its floor approximately 10,935 meters below mean sea level. The measurement carries an uncertainty of about 6 meters in either direction. That small uncertainty reflects how difficult it is to calculate depth through moving seawater across such an immense distance. For comparison, Mount Everest rises about 8,849 meters above sea level. Placed at Challenger Deep, its summit would remain more than 2 kilometers beneath the ocean surface. Water pressure at the bottom reaches more than 1,000 times the pressure experienced at sea level. Each square centimeter of a vehicle's outer surface must resist roughly the weight of a small car pressing inward. The Mariana Trench extends for about 2,500 kilometers. Challenger Deep is one especially low section within that much longer structure. The trench formed because the Pacific Plate is moving beneath the smaller Mariana Plate. This process is called subduction. Old oceanic crust cools as it travels away from the ridge where it formed. Cooling makes the plate denser. At a subduction zone, the plate bends downward and begins sinking into Earth's mantle. The bend creates a deep, narrow depression along the boundary. Earthquakes occur as rock breaks, shifts, and descends beneath the neighboring plate. Far from the Mariana Trench, the northern Gulf of Mexico contains underwater features that resemble lakes. Thick salt deposits lie beneath parts of the seafloor. These deposits formed when ancient seawater evaporated and left salt behind. Later, sediment buried the salt under the Gulf. Water moving through fractures can dissolve some of it and create extremely concentrated brine. Brine contains more dissolved salt than ordinary seawater. The added salt increases its density. When concentrated brine escapes onto the seafloor, it may flow downhill like a slow underwater stream. Depressions collect the dense liquid into pools with visible boundaries. The surface of a brine pool can ripple when a fish or research vehicle disturbs it. Mussels and bacterial mats may grow near the edge, using chemicals released by the surrounding sediments. Animals entering the concentrated brine can be harmed because its salt content and low oxygen make it difficult for most marine life to survive. Mapping such features requires multi-beam sonar. A research ship sends a fan of sound pulses toward the seabed. The pulses strike the bottom and return as echoes. Measuring the travel time allows scientists to calculate depth. Corrections account for water temperature, salinity, and pressure, because each one changes the speed of sound. Repeated passes produce narrow map strips that can be joined into a larger picture. By April of 2026, about 28.7% of the global seafloor had been mapped to the modern standard used by the Seabed 2030 project. Coarser global maps already provide a broad outline of ocean basins and ridges. Most of the floor still lacks direct high-resolution coverage from modern sonar. The largest hidden landscape on Earth is therefore partly known through gravity and partly traced by ships crossing one measured strip at a time. Sunlight disappears within the upper ocean, yet darkness does not remove every source of energy. Along cracks in young crust, seawater descends toward hot rock and returns carrying the chemical fuel needed to support life far below the surface. Along the young volcanic ridges of the deep ocean, seawater enters cracks in newly formed crust. In 1977, researchers exploring near the Galapagos Rift descended through more than 2,000 meters of water in the submersible Alvin. They expected to study geology. Instead, they found warm water flowing from the seafloor and dense groups of animals gathered around it. Large clams lay across the bottom. White crabs moved among them. Long tube worms rose from the sediment in red-tipped clusters. The discovery changed how scientists understood life in the deep sea. Until then, most known food webs seemed to begin with sunlight. Plants and algae capture light through photosynthesis and use it to build sugars from carbon dioxide and water. Animals then obtain that stored energy by eating plants or by eating other animals. Sunlight never reaches the Galapagos vents. Below roughly 1,000 meters, the ocean remains in permanent darkness. The vent communities were receiving energy through a different route. Their story begins with cold seawater sinking into fractured ocean crust. The cracks occur near mid-ocean ridges, where tectonic plates separate and magma rises to form new basalt. Basalt is the dark volcanic rock that makes up much of the ocean floor. Water moving through it is heated by hot rock deeper below. The fluid also reacts chemically with the basalt. Some substances, including magnesium, are removed from the seawater. Hydrogen sulfide, hydrogen, methane, iron, copper, zinc, and other dissolved materials may enter it. The exact mixture changes from one vent field to another. Hot fluid becomes buoyant and rises back through the crust. At some black smokers, it emerges at temperatures above 350 degrees Celsius. Water at sea level would boil far below that temperature. Several kilometers of ocean create enormous pressure, raising the boiling point and allowing the vent fluid to remain liquid. Under certain combinations of temperature and pressure, it may enter a supercritical state. Supercritical water behaves partly like a liquid and partly like a gas, allowing it to move through rock and carry dissolved material very effectively. The vent fluid looks black when it enters the cold ocean. The color comes from tiny mineral particles rather than smoke from fire. Hot fluid carrying dissolved metals meets seawater that may be only a few degrees above freezing. The sudden cooling changes which substances can remain dissolved. Iron, sulfur, copper, and zinc combine into solid mineral compounds. Clouds of these particles create the dark plume. Some settle around the opening and build a chimney. A chimney can grow quickly while fluid continues passing through it. New layers form along cracks and outer surfaces. Sections may break, block the vent, or redirect the flow toward a new opening. The process resembles mineral precipitation at Dallol and crystal growth at Naka, though the deep ocean version occurs under far greater pressure and much faster temperature change. Life gathers where the hot chemicals mix with oxygenated seawater. Certain bacteria and archaea use chemical reactions involving hydrogen sulfide, hydrogen, methane, or iron to obtain energy. Archaea are single-celled organisms that resemble bacteria in size, but belong to a separate branch of life. These microbes use their chemical energy to turn carbon dioxide into organic material. The process is called chemosynthesis. Photosynthesis begins with light energy. Chemosynthesis begins with energy released by chemical reactions. Giant tube worms provide one of the clearest examples of this partnership. Adult tube worms have no mouth and no working digestive tract. Inside the body is a specialized organ called the trophosome. It contains billions of symbiotic bacteria. Symbiosis means that two different organisms live closely together. The worm's red plume absorbs oxygen and hydrogen sulfide from the surrounding water. Its blood carries those chemicals to the bacteria. The bacteria use them to make organic molecules, which feed both the microbes and the worm. Vent mussels and clams may also contain chemosynthetic partners inside their tissues. Other animals graze on microbial mats or prey on organisms gathered around the vents. These communities still have some connection to the surface. Oxygen reaches the deep ocean through global circulation, after entering the sea from the atmosphere, or being produced by photosynthetic organisms above. Some falling organic material also arrives from shallower water. The central source of local food production, however, comes from rock-water chemistry powered by Earth's internal heat. A dark sea floor can therefore support crowded communities without direct sunlight. Liquid water, usable chemicals, and suitable temperatures still set clear limits on where that life can exist. The same materials moving naturally through vents can now be redirected by people on a very different scale, altering rivers, lakes, fuel deposits, and entire landscapes visible from orbit. Between Kazakhstan and Uzbekistan, the Aral Sea once covered a broad inland basin in Central Asia. During the early 1960s, it ranked among the 4 largest lakes on Earth. Fishing towns stood along its shores, and ships carried catches of carp, pike perch, and sturgeon to nearby processing plants. 2 major rivers supplied most of its water. The Amu Darya approached from the south after flowing from the mountains of Central Asia. The Sir Darya entered from the northeast. Both rivers carried snowmelt and rain toward a basin with no outlet to the ocean. Water left the Aral Sea mainly through evaporation. For the lake to remain near the same size, river inflow had to replace much of the water rising into the dry air. That balance changed during the Soviet period. Large irrigation projects diverted river water into canals and fields, especially for cotton and other crops grown across dry parts of Central Asia. Some canals stretched for hundreds of kilometers. Many were unlined, allowing water to soak into surrounding soil or evaporate before reaching farmland. By the 1960s, far less water was reaching the Aral Sea. Evaporation continued across its wide surface. The lake began losing more water each year than the rivers supplied. Its shoreline slowly moved away from ports and villages. A harbour that once opened onto deep water could eventually stand kilometers from the nearest shore. The retreat did not happen during one unusually dry season. Satellite images recorded the change across several decades. As the water level fell, the remaining lake became saltier. Fresh river water had once diluted the salts already present. Reduced inflow allowed evaporation to concentrate them. Many fish species could no longer survive or reproduce under the changing conditions. Commercial fishing declined. Boats were left on dry ground, and processing towns lost much of the work that had supported them. The shrinking lake gradually separated into smaller bodies of water. The northern portion became known as the North Aral Sea. The southern portion divided again into western and eastern lobes, with narrow channels and shallow areas appearing between them. Former islands became attached to the mainland as surrounding water disappeared. By 2014, the eastern lobe of the South Aral Sea had completely dried during the modern satellite record. The exposed basin appeared pale and empty from orbit. Water returned to parts of it during some later wet periods, so its condition continued to shift with river flow, rainfall, and evaporation. The long decline had already created a new landscape. Large areas of former lakebed became the Aralcombe Desert. Salt crystals remained within the dry sediment. Agricultural chemicals and other pollutants carried into the basin over many years also settled in parts of the lakebed. Strong winds could lift fine particles and carry them across surrounding communities and farmland. Dust from the exposed ground affected air quality and deposited salt onto soil beyond the former shoreline. Loss of the lake also changed local temperature and humidity. Large bodies of water warm and cool slowly, helping soften nearby seasonal extremes. As the Aral Sea contracted, summers near the old shoreline could become hotter and winters colder. One part of the basin later showed that carefully directed engineering could still change the outcome. Kazakhstan completed the Kok-Aral Dam in 2005. The structure helped hold water from the Sirdarya inside the North Aral Sea, instead of allowing it to drain southward into the lower basin. Water levels rose, salinity decreased, and several fish populations began recovering. The improvement remained regional. The dam supported the smaller northern lake, while much of the southern basin stayed severely reduced. The Aral Sea shows how a change in water flow can spread through an entire system. River diversion altered lake level and salinity. Those physical changes affected fish, employment, dust, and the climate experienced by nearby communities. A decision made far upstream eventually redrew coastlines visible from space. Centralia followed a different path through the same basic pattern of long consequence. An attempt to manage waste was followed by fire entering an underground coal system. Decades later, heat and gas still move through abandoned passages beneath the town. In Central Asia, irrigation changed. where water traveled. In Pennsylvania, disturbed mine workings changed where fire could spread. Both landscapes continued responding long after the original human actions. Once change reaches that scale, understanding the mechanism becomes the starting point for deciding what can still be repaired, contained, protected, or safely left alone. Once a landscape has changed, the most useful response begins with the process still moving through it. At Lake Nyos, carbon dioxide continues entering deep water from geological sources beneath the crater. Blocking every fracture below the lake would be extremely difficult. The gas source lies underground. Its exact pathways are complex, and pressure would continue building if the carbon dioxide remained trapped. Engineers therefore chose controlled release. A pipe lowered into the deep water began permanent degassing in 2001. Water rich in dissolved carbon dioxide was first pumped upward. As it rose, pressure decreased and bubbles formed inside the pipe. The gas-filled water became less dense than the surrounding lake water, allowing buoyancy to keep the flow moving. Buoyancy is the upward force that makes a less dense material rise through a denser one. Once the fountain started, the lake supplied much of the energy needed to maintain it. Carbon dioxide escaped gradually into moving open air instead of accumulating in a deep layer. Later pipes increased the rate of removal. The system reduced risk by releasing stored pressure slowly, while the geological gas source remained in place. A different intervention changed the flow of water in the Aral Basin. Kazakhstan completed the Koch-Aral Dam in 2005 across a narrow connection between the North Aral Sea and the lower southern basin. Before the dam, water entering from the Sirdarya could continue southward and spread into areas where evaporation removed much of it. The barrier helped retain more water within the smaller northern lake. Its level rose by several meters during the first years after completion. Salinity declined as fresh river water diluted the remaining salt. Fish species that could tolerate the improved conditions returned or increased, and commercial catches recovered in several communities. The shoreline also moved closer to the port town of Aralsk, though it remained far from its position before the wider sea began shrinking. This project improved one part of the system. It did not refill the former South Aral Sea or recreate the entire lake that existed during the early 20th century. The available river flow could support a smaller managed basin more successfully than the former full area. At Centralia, engineers faced heat moving through a maze of coal seams and old mine passages. The fire's boundaries changed underground. Hidden openings supplied oxygen, while collapsed workings made excavation dangerous. Smoke and carbon monoxide could emerge far from the most visible hot ground. Early attempts included digging barriers and sealing sections of the mine, but the fire continued spreading through connected coal. A complete excavation would have required removing enormous amounts of rock and locating every burning pathway. Authorities eventually focused on reducing human exposure. Most residents accepted government-funded relocation during the 1980s and 1990s. Homes were demolished, streets were closed, and unstable areas were left with very few people nearby. The coal fire was not fully removed. Relocation separated residents from ground collapse, gas, and heat that could not be controlled with confidence. Surtsey required almost the opposite kind of management. The island's scientific value depends on allowing wind, ocean currents, and animals to deliver organisms naturally. Human visitors could easily carry seeds in mud on a boot. Insects might arrive inside clothing, food containers, or equipment. A single introduced plant could reproduce and blur the record of how species reach the island. Access is therefore tightly restricted. Researchers follow cleaning rules, limit what they bring ashore, and remove waste after visits. The goal is to reduce human disturbance while waves, birds, microbes, and plants continue shaping the island. Each location requires a response matched to its active mechanism. At Nios, gas is released before it can build to a dangerous concentration. The North Aral retains river water that would otherwise escape into a much larger drying basin. Centralia's remaining residents were moved away from a hazard whose underground path could not be reliably removed. Surtsey is protected through restraint because unnecessary action would alter the process being studied. Success can be measured through lower gas concentrations, safer communities, reduced salinity, returning fish, or an ecological record kept free from accidental introductions. A landscape may still look damaged or dangerous, while a carefully chosen intervention prevents further loss. Those choices depend on measurements taken over long periods. Gas concentrations must be tracked beneath a lake. Changing shorelines need repeated maps. Heat and ground movement require sensors. Plant and animal arrivals must be recorded with care. Understanding where a system is heading requires instruments that can follow changes too slow, distant, deep, or widespread for unaided human senses. A shoreline shifting over decades cannot be understood from one visit. The Aral Sea became one of the clearest examples of how repeated observation can reveal change. Since 1972, Landsat satellites have photographed Earth through a joint program operated by NASA and the United States Geological Survey. Each satellite passes over the same regions again and again. Images taken years apart show the Aral Sea retreating from ports, dividing into smaller basins, and exposing pale sediment across its former floor. NASA's Terra satellite added another long record after its launch in 1999. An instrument aboard Terra, called the Moderate Resolution Imaging Spectroradiometer, observed the Aral Basin in many parts of the light spectrum. Human eyes detect only visible wavelengths. Satellite sensors can also measure infrared light and other wavelengths reflected or released by the surface. Water absorbs some wavelengths strongly, so it often appears dark in processed satellite images. Healthy vegetation reflects near-infrared light in a distinctive way. Salt, bare soil, clouds, and warm ground each produce different signals. Scientists combine selected wavelength bands to make features easier to separate. A sequence of these images reveals the pace and direction of change more clearly than a single photograph ever could. Brief events require a different kind of instrument. The lightning imaging sensor traveled aboard the Tropical Rainfall Measuring Mission, which launched in 1997. From orbit, it detected tiny flashes of light produced inside thunderstorms. The sensor observed large areas of the tropics and subtropics as the satellite traveled around Earth. One flash lasted only a fraction of a second, yet millions of detections collected over many years created a global map of lightning activity. Researchers compared how often flashes occurred within equal areas. That long record identified the Lake Maracaibo region as the world's leading lightning hotspot in the analysis. A person on the ground might witness one storm. The satellite record revealed the pattern built by thousands of nights. The temporary lake in Death Valley required measurements of height as well as area. The Surface Water and Ocean Topography mission launched in December of 2022. Its name is often shortened to SWOT. The satellite carries a radar system designed to measure the elevation and spread of water across wide strips of Earth. Radar sends radio waves toward the surface and records the returning signal. SWOT uses two separated radar antennas. By comparing the signals received at each antenna, researchers can calculate the height of the reflecting surface. This method is called interferometry. The word describes the combining of related signals to measure small differences in distance. When SWOT passed over Badwater Basin in early 2024, it measured the surface of the temporary Lake Manly. Scientists compared that water height with an existing map of the land below. The difference gave an estimate of depth, even across parts of the lake that were difficult to reach safely on foot. Radar works well for an exposed water surface. Several kilometers of seawater block. Ordinary satellite photography from seeing the ocean floor. Detailed mapping there depends on sound. A multi-beam sonar system is mounted beneath a research ship. Its transducer array converts electrical energy into sound pulses and sends them downward in a broad fan. The seabed reflects part of that sound back toward the vessel. Travel time reveals distance. The angle of each returning echo shows where that point lies beside or beneath the ship. Water temperature, salinity, and pressure all change the speed of sound. So researchers measure those conditions and correct the calculations. Each passage of the ship produces a map strip called a swath. Many overlapping swaths gradually reveal a trench, ridge, seamount, or brine pool. Different tools answer different parts of the larger story. Chemical probes lowered into Lake Neos measure carbon dioxide and temperature at selected depths. Seismometers record ground vibrations caused by earthquakes and moving magma. Drilling equipment retrieves sediment cores from beneath lakes, ice, and ocean floors. Microscopes reveal cells living in Antarctic brine or around hydrothermal vents. Every instrument converts a signal into evidence. Reflected light can show a retreating shoreline. A brief optical flash becomes a lightning count. Radar phase produces the height of a lake. Sound travel time becomes the depth of an unseen mountain. Knowledge grows when those measurements are repeated, compared, and checked against observations made by other methods. Some of the same instruments are taken into Earth's driest deserts, coldest ice, and most acidic waters before being prepared for destinations much farther away. The instruments used in deserts and beneath ice often serve two purposes. They help researchers understand difficult places on Earth, and they test methods that may later travel to another world. Scientists call a useful Earth location a planetary analog. An analog reproduces selected conditions found or expected elsewhere. One site may offer extreme dryness. Another may contain acidic water, iron minerals, buried ice, or chemical energy in darkness. No location on Earth matches Mars, Europa, or Enceladus in every detail. Gravity, atmosphere, radiation, pressure, and geological history remain different. The value comes from isolating a specific challenge and learning how an instrument responds. Chile's Atacama Desert has become one of the most important testing grounds for Mars exploration. Some soils in its driest regions contain very few detectable living cells. Salt accumulates near the surface. Ultraviolet radiation is intense, and liquid water may be absent for long periods. These conditions make biological signals difficult to find. They also create a useful place to test whether a rover can travel, drill, collect material, and recognize faint signs of life without constant human control. A rover named Zoe carried out fieldwork there during a NASA-supported campaign in 2013. Zoe traveled autonomously for roughly 30 kilometers. Autonomous movement means the rover used onboard computers and sensors to choose parts of its route, rather than waiting for a person to guide every turn. It carried a drill capable of reaching about 1 meter below the surface. Subsurface samples matter because sunlight and radiation can damage organic material near the top of the soil. Deeper layers may preserve water, salts, cells, or chemical traces for longer periods. Later work through the Atacama rover Astrobiology Drilling Studies program tested a drill that could reach approximately 2 meters. The system also practiced transferring samples from the drill into scientific instruments. Navigation software had to avoid rocks and steep ground. The rover needed to keep samples separate and prevent material from one depth contaminating another. Onboard tools then examined the soil for molecules, minerals, and possible biological signals. Every step copies part of a future planetary mission, where a delayed radio signal prevents scientists on Earth from controlling each movement in real time. Southwestern Spain provides a different comparison. The Rio Tinto flows through an acidic region rich in iron and sulfate minerals. One of those minerals is jarosite, an iron sulfate that commonly forms where acidic water interacts with iron-bearing material. In 2004, NASA's Opportunity rover detected jarosite on Mars. The discovery showed that acidic liquid water had affected Martian rocks in the distant past. Rio Tinto helps researchers study how minerals form under similar chemical conditions and how traces left by microorganisms might become trapped or altered within them. The presence of the same mineral in two places does not show that the same biology occurred. Jarosite records chemistry involving water, iron, sulfate, and acidity. Researchers must search for separate evidence before making any claim about life. Dallol provides an equally important lesson about environmental limits. Some pools contain liquid water under intense heat, extreme acidity, heavy salinity, and high metal concentrations. Several nearby environments support microorganisms. The harshest pools have produced disputed or negative evidence for active life, depending on the exact location and method used. Liquid water, therefore, provides only one requirement. Cells also need chemistry that allows proteins, membranes, and genetic material to function. Too much salt can pull water from a cell. Extreme acidity can damage biological molecules. High concentrations of certain metals can disrupt essential reactions. Astrobiology studies places where organisms survive and places where the combination becomes too severe. Beneath thick ice, Earth offers comparisons for the ocean worlds farther from the Sun. Europa, one of Jupiter's moons, probably contains a global salty ocean beneath an icy shell. That ocean may rest above a rocky seafloor. Researchers study Antarctic brines to understand how liquid can persist below ice and how chemical traces might move through cracks toward the surface. Enceladus, a small moon of Saturn, releases plumes containing water vapor, ice particles, salts, and organic compounds. Measurements have also found molecular hydrogen, which may form when water reacts with warm rock. Similar water-rock reactions supply chemical energy around some hydrothermal vents on Earth. No vent has been directly observed on Enceladus, and no life has been detected on either moon. Earth's vents and frozen brines help scientists decide which measurements could test those possibilities. The strangest places on this planet become rehearsal grounds because they expose conditions that ordinary landscapes keep hidden. Looking outward eventually sharpens the view back home, where familiar physical rules have produced environments that once seemed beyond imagination. The same physical rules appear in places separated by oceans, climates, and thousands of kilometers. At Dallol, heated water carries dissolved minerals upward through salt and volcanic rock. Black smokers on the ocean floor also release mineral-rich water, although they operate beneath immense pressure and in complete darkness. In both settings, a rapid change in temperature or chemistry causes dissolved material to become solid. Yellow crusts form across an Ethiopian hydrothermal field. Metal sulfides gather into chimneys above cracks in oceanic crust. The surroundings look entirely different, while precipitation from chemically active water connects them. Salt creates a second connection. At Salar de Uyuni, repeated evaporation left a white crust across more than 10,000 square kilometers. Inside Taylor Glacier, concentrated salt allows ancient brine to remain liquid below the normal freezing point of fresh water. One landscape preserves evidence of water that vanished into the atmosphere. The other shelters water that remains hidden beneath ice. Isolation also works at several scales. Ocean crossings limited the movement of plants and animals reaching Socotra, allowing many populations to develop separately. Lake Baikal enclosed freshwater organisms inside an ancient rift basin for millions of years. The result in each place is high endemism, meaning many species occur naturally nowhere else. That uniqueness also concentrates risk, because a small global range gives a species fewer places to survive disturbance. Density shapes quiet layers that can remain separate for long periods. Cold, gas-rich water accumulated beneath Lake Nyos because it was denser than the water above. Concentrated brine settles into pools on the floor of the Gulf of Mexico because extra dissolved salt makes it heavier than normal seawater. Movement begins when pressure, mixing, or slope disturbs those layers. A calm surface may therefore sit above water, with a very different chemical character. Some of the strangest places also show change within a human lifetime. Surtsey rose above the North Atlantic beginning in 1963, gained plants and nesting birds, and then began losing its softer shoreline to waves. The Aral Sea moved in the opposite direction, as reduced river inflow allowed evaporation to shrink one of the world's largest inland water bodies. Its retreat exposed a new desert, while engineering later helped part of the northern basin recover. These landscapes appear dramatic because ordinary processes have been enlarged. Iron oxidation leaves a reddish stain on a metal tool. The same chemical family of reactions colors the outflow at blood falls. Evaporation removes water from a shallow dish and leaves dissolved material along its edge. Across a closed basin, repeated evaporation builds salt layers thick enough to cover the horizon. Carbon dioxide remains dissolved inside a sealed drink under pressure. In a deep layered lake, the same rule allowed geological gas to accumulate on a scale that affected entire valleys. Rainwater, containing weak carbonic acid, can roughen a limestone surface. Given fractures, flowing water, and enough time, that mild chemistry can open caves, underground rivers, and sinkholes more than 600 meters deep. Scale changes the result. Concentration increases the strength of an effect. Duration allows small changes to accumulate. Feedback can make a process speed up after it begins. Clear scientific limits remain important. Liquid water creates an opportunity for life, while temperature, acidity, salt, metals, and available energy decide whether cells can function. Isolation can support biological variety, while leaving rare species exposed to sudden change. Engineering can lower gas levels, retain water, or move people away from danger, without rebuilding every earlier condition. A landscape can be scientifically understood, even while its full-size history or internal detail remains unmeasured. Exploration and explanation describe different kinds of knowledge. Much of the ocean floor still lacks direct modern sonar coverage. As of April 2026, less than 1/3 had been mapped to the current international standard. Scientists already understand the broad processes that create trenches, ridges, seamounts, and abyssal plains. New mapping adds precise shapes, depths, and features to that framework. The locations themselves continue changing. Uyuni shifts between dry salt crust and shallow seasonal water. Racetrack playa may wait through many winters before stones move again. Surtsey loses loose ash while harder basalt remains. Mineral chimneys grow, break, and redirect hydrothermal flow in the deep ocean. Strangeness often belongs to one moment inside a longer process. A useful way to understand such a place begins with careful observation. Color can reveal a mineral or chemical reaction. Shape may record flowing water, moving ice, or collapsing rock. The material shows what was available. Its energy source explains what kept the system moving. Water, gas, sediment, heat, and living organisms enter or leave at measurable rates. Time allows those movements to build a result large enough to become a landscape. Across the mirrored salt of Uyuni, a few centimeters of water can seem to hold the whole sky. At Taylor Glacier, iron-rich brine reaches daylight after a long passage beneath ice. A forest grows below the rim of a Tiankeng, where weak acid once widened hidden cracks. Far beneath the ocean, hot water meets cold seawater and builds a mineral chimney grain by grain. Familiar laws produced each unfamiliar view. Water moved through rock. Minerals responded to pressure and temperature. Organisms changed during isolation. Energy rose from the planet's interior. quiet processes continued long enough to become entire worlds.